So, good morning, everyone. My name is Nishiyama, and then you can see here the first author or the leading researcher of this project is Mr. Yamada, but he couldn't make it. So then instead of him, I will present this project to you. So then the second author, the Professor Masanori Tani, he is an associate professor of our lab, and myself. So what I did in this project was to write the proposal and obtain the money. Okay? So then anyway, next. So these are the contents of my presentation. And then you can see here, we have the paper, the same title of this presentation in the ACI Structure Journal last year. So then if you are interested in this project, so you can have the paper, you can have a look at the paper. Okay. So the first introduction. So several years ago, we conducted a shaking table test in E-defense. Probably you know what the E-defense is. So then this is one of the biggest shaking table facility in the world. And then there we constructed a 6-story, 30% scale reinforced concrete building. Then we applied the shaking to this building. So let me show you the short video where. So how we are. So we applied the earthquake record recorded in during the Kobe earthquake in 1995, and then during the shaking, we observed this type of failure of the walls, right? So then the wall failed differently or different from what we expected. So then so of course those walls failed in shear, but we had seen the slippage at the bottom of the wall. So then after this shaking table test, we found that the boundary condition or forces around the wall should be considered. So then this is a schematic figure of the wall, and then this is the main direction of the wall. We call in-plane direction. And then the out-of-plane direction, we usually have the beams. And then from those other shear force of the beams, this wall has a axial force. And of course, as the earthquake load applied to in this direction, the axial load on this wall varies. And but in Japan, we usually use this design equation for design the walls. So at present, structural performance evaluation method of RC members considering in tri-directional forces in earthquakes has yet to be established. you can see here this is a concrete contribution and the shear reinforcement contribution, or horizontal and vertical reinforcement contribution. And then also here you can see the contribution of the axial force. So then but we don't know how much axial force, or we don't know how this axial force have an effect on the shear behavior of the wall. So then the objectives of this project is investigating the effects of axial load condition and the lateral bidirectional loading path on the shear capacity of shear walls. And then we conducted the loading tests on shear wall specimens subjected to bidirectional loading under various axial load. So the first, the outline of experiment. This is the specimen which we used in this project. This is a 30% scale shear wall with. So we constructed the several specimens, and they were identical. They were identical, so that they have the same dimensions and the same reinforcing arrangements. And then this project started several years ago, and then we constructed several specimens. So then but today I want to focus on these 4 specimens. And then you can see here the experimental parameters as the axial load, and then the out of plane, and then the in plane drift ratio. So this is a ratio. Here you can see you can see the O over I drift ratio. This means the out of plane drift angle divided by in plane drift angle. Okay? So then this 0 means the in plane loading only, and then the 1.5 and 3.0. So then the out of plane drift angle is 3 times in plane drift angle. Okay? And then this is a axial load ratio, and then these 2 constant axial load ratio, and then we applied varying axial load, like the 0 to 0.2 AGF prime C, then the AG, the gross sectional area of concrete, and F prime C is the compressive strength of concrete. And then here we apply the tensile force, tensile axial load on the column, on the wall. So then the tensile force was defined as the ratio to the tensile force of the reinforcement. So the ACG means the gross sectional area of longitudinal rebars, and Fy is the yield strength of longitudinal rebars. Okay. So we constructed the specimens in several by the different concrete. So then the compressive strength of concrete are different. When from 21.9 to 28.9 MPa. So then when we compare the results of these specimens, then we have to consider the difference between these compressive strength. And then this figure shows the axial load variation. And then here you can see the axial load, and then the x-axis indicates the out-of-plane lateral load. So as I showed you, then we considered this type of framing. So then the axial load on the wall should have a relation to the shear force in the beams in the orthogonal direction. So then the axial load is related to the out-of-plane lateral load. So then this is the start of the axial load. This means the service load, and then the axial load is increasing up to the 0.2 AGF prime C, and then the axial load is now constant. And this is the compression side. And the tensile side, tension side, we have two routes. One is to the zero axial load, and then one is the tensile axial load, defined by the ratio to the tensile force in the reinforcement. And then there are some ways to apply lateral loading. So then we have to define, or we have to decide how we apply the load. So then this is the way we apply the load. This is the starting point, and then first we apply the out-of-plane loading to the up to this point, and then we apply the in-plane load. And then after unloading the out-of-plane load, and then unload the in-plane load. And then we go this way, and this way, and this way, and go back to the origin. So we call the figure of 8 loading schematic loading path. So there are some ways to apply this type of bidirectional loading, but we chose this type of loading path. And then this is just as I showed you in the previous slide, and then and then, okay. Here, you can see the in-plane direction. The upper figures show the shear strength of the wall in plane shear strength in the in-plane direction. So then this was calculated by the design equation, and also the bottom figures is the fracture strength of the wall. So then the shear strength is smaller than the fracture strength. So then these walls were expected to fail in shear, right? And this is the out-of-plane direction, and then the shear strength is larger than fracture strength. So then these in this direction, the columns were expected to fail in fracture. And this is a loading setup. And then you can see here the specimen, right? And then we use the 6 oil jacks. to apply the axial load and then the two directional horizontal loads. And then this is the photo of the loading system, and then the axial load applied here, and then the in-plane load and out-of-plane load. And then just to help you understand how we apply the load, please look at this. This is a specimen, and the being applied load. And then here you can see the out-of-plane direction, and then also the in-plane direction load, and then the drift angle relationship, and this is the out-of-plane. And then here you can see the axial load variation, and then this shows the orbit of the in horizontal plane. So now you can see the moving of the specimen. Okay. So, for example, it goes this way and then that way. So then the loading system is a little bit complicated, but complicating, and then we control the whole system, and then we realized this type of loading path. And experimental results, as I showed you in the video, so we could have the loading path like this, and then also the axial loading path was realized. And then this is a specimen. It's called WB15 C20T00. This means that the over I drift ratio. So the out of plane, in plane drift ratio is 1.5, and the axial load ratio from 0 to 0.20 AG F prime C. And then you can see shear cracks developed and the fracture cracks developed, and then this shows the in-plane lateral load, in-plane drift angle. This figure shows the out-of-plane load and then the out-of-plane drift angle. Okay, let me show. And then this is when we had the OI drift ratio of 1.5, and then this is this is the after test of the same specimen. So you can see the shear crack here, and then this is the final figure of the specimen. And then this is a different one. The axial load ratio is different. So then we apply the tensile force to this wall. And then here you can see the shear cracks developed and fracture cracks in the out of plane direction. And then this is the drift ratio of 0.5%. And then this is after the test. So we had a big shear crack here, and this is the end of the test. And then in this case, we apply the OI drift ratio of 3.0. So then out of plane drift was 3 times the in plane drift. The shear cracks developed and the fracture cracks developed, and then this is the figure at the drift ratio of 0.5%. And then this is after the test. You can see here the shear crack here or this in this direction. So this figure compare the experimental results between 3 specimens, which had the same out of plane in plane drift ratio, but the axial load ratio is different. So this red line shows the specimen of 0.2 LGF'(C) constant axial load, and this green line shows the axial load ratio being varying between 0 to 0.2, and then the blue line. This is shows when we apply the tensile force in the wall. So as you can see here, when we apply the tensile force in the wall to the wall, then we had a smaller capacity, shear capacity in the in plane direction. So then this y-axis shows the shear capacity, but as I said, the concrete strengths were different between the specimens. So then we standardized the capacity by dividing the capacity by dividing the capacity first by the sectional area of the wall, and then and also by the tensile force, tensile strength of the concrete. So then the y-axis shows the 1.0, 2.0, and then we can now compare those specimens. And then if we have the constant axial load, the capacity is the largest, like this. And then this figure shows the comparison in terms of out of plane in plane drift ratio. So then we had 2 types of out of plane in plane drift ratio. So then 1.5 and 3.0, and hi. Hi. Well, I almost now approaching the conclusion. Right. And then in this specimen, the difference is very small. So then in this case, even if we apply the out of plane drift, but that did not influence the capacity of the in-plane capacity of the wall. So okay, let me skip this one. So today I just showed you the experimental results of we conducted on the shear wall specimens, and then we found the bigger difference between the maximum axial load and the minimum axial load was the lower the maximum load capacity the specimen showed. So that as the design equation suggested, of course the axial load had the much influence on the capacity in the wall. And then the out-of-plane deformation did not affect in-plane maximum load capacity. But before this project, we conducted another several specimens, and then we found the difference between the in terms of the out-of-plane and then the in-plane direction deformation ratio. And now, with analytical research, we try to figure out the resistance mechanism of the shear walls under in axial loading. So this is the end of my presentation. Thank you very much.
Thank you. Now, the session is open for discussion. One or two questions for limit of time. Yes. Using the microphone there. Thank you.
Okay, is there any reason why you used 1.5 and 3.0 of drift ratios as a variation in this research, and how, as where from those numbers?
Yeah. Yes. So, you know, the shear failure may occur at the drift ratio of 1/200 or 1/250 in the in-plane direction. So then and then in out-of-plane direction, we assume that we had a moment frame or moment resisting frame. So then the 1/200 times 3 is the 3 1/60 or 1/50, right? So then we consider that the maximum or the deformation we usually had. That the deformation we assume that the moment resting frame fails in flexion. Right? So that's why we chose 3. That's a maximum. And then the 1.5 is the 0 and the 3.0. That's in between these two numbers.